Our next lesson consists of solving absolute value, this time for inequalities. So if I want to think of, or if I want to find solutions for x, where the absolute value, after taking the absolute value, I get numbers less than 2. All right, so 1 is less than 2. 0 is less than 2. A half is less than 2. 1.5 is less than 2. 1 3/4 is less than 2. But since I'm taking the absolute value, we can include negative numbers. -1 is less than -2, -half, -1.5. Anything bigger than -2 we can't include. We can't include -3 because once I take the absolute value of -3, I get +3, and 3 is not less than 2. So I can go in all the way up to -2 and all the way up to +2. And it includes all numbers in between. And this should look familiar from compound inequalities. This is an and statement. So my solution is between -2 and +2. So remember, when we write it like this is saying x is greater than -2, but at the same time it's smaller than 2. So it's somewhere in the middle. It's in between. So x is between -2 and +2. This changes a little bit for greater than symbols. So I want to know all values that are greater than -2 after taking the absolute value. So 3 is greater than -2. 4 is greater. 2.5, 3.5, 4.5, 5, 6. All right, all numbers that are bigger than 2. But now, because I'm taking absolute value, I can include negative numbers. So if I take the absolute value of -3, I get 3, and 3 is greater than 2. I take the absolute value of -4, I get 4. 4 is greater than 2. So -3, -4, -2.5, -3.5, -5, -6, -2.1. All right, so I can shade in all values that are bigger than 2. I can also shade in all values that are less than -2. This type of graph should also look familiar from compound inequalities. I have created an OR statement. So my solution set for the absolute value of x is greater than 2 is x is less than -2 or x is greater than 2. So to sum that up, if we're taking the absolute value of some expression, so I just put ax plus b, a and b can stand for any variable, and it is less than c, for c being greater than 0. It's important that I put c as being greater than 0 because we don't want there to be any negative values, because that is still no solution or all real numbers depending on your inequality. Then I can split that up into 2 inequalities again, one to represent the positive, one to represent the negative. So when I solve, I'm going to have ax plus b is less than c, and since less than goes along with and statements, ax plus b is greater than -c. Notice that when I am working with the negative side, I flipped my inequality. Just like when we multiply or divide by a negative, our inequality changes. The same is true with inequalities for absolute value. All right, my second key concept, the absolute value of ax plus b is greater than c. Once again, we have to say c is greater than 0. Then I can split into 2 sides, my positive half and my negative half. This time we form an OR statement because greater goes with OR. So ax plus b is greater than c, that's the original, or ax plus b is less than negative c. Notice on the negative side, again, we flipped our inequality. So our first example is less than, and because it's a less than inequality, we already know that it's going to be an and statement. I have nothing on the outsides of my absolute value bar, so I'm going to go ahead and solve right away. So I'm going to split into my positive version and negative. For my positive, I write exactly how I see it. 2w minus 1 is less than 11. For my negative, I have to flip my inequality and rewrite 11 as negative 11. So that is going to be 2w minus 1 is greater than negative 11. Then we solve just like we would solve any normal two-step inequality. So I add 1 to both sides. 2w is less than 12. Divide by 2. And 1/2 of my answer is w is less than 6. I solve a second time with greater than negative 11. So I add 1 to both sides. 2w is greater than negative 10. Divide by 2, and w is less than negative 5. So I'm going to put negative 5 on the left and 6 on the right because number lines go from least to greatest. So my I made a mistake. Greater than. I'm not sure why I flipped it. We didn't divide by a negative number. All right, so w is greater than negative 5. So I want to represent all numbers that are bigger than negative 5. And w is also less than 6. So all numbers that is less than 6. Now remember, and statements are the union or the intersection. If you remember that, you do not have to double graph and see what they have in common. Just know that it is in between the two values. So I like to rewrite my statement as an and statement. So negative 5 is less than w, which is less than 6, meaning that w's solutions are in the middle of negative 5 and 6. Our last example is an or statement. So that means that my graph's going to be going off in different directions. Before I start, though, my absolute value bars are not isolated. So I want to subtract 1 from both sides. And then I want to get rid of the 4 out in front by dividing. So I'm left with the absolute value of 2x minus 5 is greater than 5. Now that my bars are isolated, I can split into the positive, into the negative sides. Positive is exactly how you see it. 2x minus 5 is greater than 5, or on my negative side, 2x minus 5 is less than negative 5. Notice that I flipped when I rewrote my negative value. All right, then we're just going to solve. I add 5 to both sides, so 2x is greater than 10. Divide out by 2, so x is greater than 5. On my second side, I'm going to add 5. 2x is less than 0. Divide out by 2, and x is less than 0. So my final answer is x is greater than 5 or x is less than 0. So when I go to graph this, there's my 0, there's my 5. So I need to represent all values greater than 5. And all values that are less than 0. So in an or statement, it can be either or. Okay, so so all possible solutions are anything that are less than 0, anything that are less than 5, and both sets of those would work.